and a world-renowned expert in space radiation effects and space environment modeling, where she led strategic work in technology, radiation R&D, and space missions. She was instrumental in the creation and implementation of the NASA Living with the Stars program, which included key projects on the space environment radiation effects on materials, microelectronics, detectors, and sensors present on spacecrafts, and the change and discharge of spacecraft, paving the way, in fact, to modern space missions. Janet worked for almost 15 years at NASA Goddard Space Flight Center, where she also served as chief of the Electrical Engineering Division. At Goddard Space Flight Center, she was responsible for the delivery of spacecraft and instrument avionics to several of the NASA science missions. And some of them are including the Solar Dynamics Observatory, the Swift Burst Alert Telescope, the Lunar Reconnaissance Orbiter, Global Precipitation Measurement Mission, Magnetospheric Multiscale Mission, and last but definitely not least, the James Webb Space Telescope. So Janet is a fellow of the Institute, so the IEEE, was the president of the Nuclear and Primary Science Society for 2013 and 14. So she was, of course, past chair of the Society Radiation Effects Steering Group. And in 2014, she was awarded the IEEE MPSS Radiation Effects Award and the very prestigious NASA Goddard Space Center's Robert Goddard Award of Merit. So apart from that, Janet served as MPSS WAE liaison for many years. She's a renowned teacher. She's organizing conferences. And today, of course, she's representing the societies.
Next stop, North Philadelphia.
So the talk of Janet today will be space, environments, and effects. Thank you very much, Janet, to be with us today, and the floor is yours.
Thank you, Cinzia. So I said a summary. Obviously, you did your homework. All right, so can everyone see? It looks like I'm up and running. Well, I had the opportunity to see the two previous presentations in this series, and I have to say the speakers were outstanding. I hope the people attending today will also attend some of the others. Those speakers set a very high mark. So I'm going to talk about space radiation environment and effects, and I will kind of weave that into my career, which I was at Goddard for over 30 years. So I consider myself a high mileage, low tread engineer. This is an overview of my professional experience. I was at Goddard Space Flight Center. First as a radiation hardness assurance engineer. That's where I really learned my technical stripes. As Cinzia mentioned, I got involved with the Living with the Star program. So I was the project manager and project scientist for the test bed part of that program. That's a flight test bed. I was concerned about not having representation for our radiation effects people in branch management. So I was lured into branch management as associate branch head, and then I became the branch head. And eventually, I guess I earned enough technical stripes and earned enough about avionics systems that I became the division manager for electrical engineering. And then I was an emeritus scientist after I retired for a few years. More recently, I was appointed to the board of advisors for a small startup aerospace company. And then I am doing, I'm on review panels for proposals to NASA for new missions as a subject matter expert. So I really came back home to radiation effects recently. This is an overview of my my IEEE activities. I have been involved for many years in attending and helping to organize the Nuclear and Space Radiation Effects Conference. And in 2006, I was asked to be the general chair of the conference, which was a really fun job. I was elected to the administrative committee of the MPS Society. And there I was then elected society president. And I had the opportunity to also be the Women in Engineering liaison. And now I was elected to the Radiation Effects Steering Group. I just finished my service, 3-year service as the executive chair, and now I'm the past chair. Because I spent so much of my career at Goddard, I kind of want to get an overview of Goddard Space Flight Center. It's in Greenbelt, Maryland. We also have the launch facility on Wallops Island, Virginia. And Goddard is the home to the largest organization of combined scientists, engineers, and technologists in the United States. So we build and operate spacecraft, instruments, and new technologies to study the whole gamut of the space Of course, Christmas morning, I got up early to watch the spectacular launch of James Webb Space Telescope. That was a long, long development project, and it was really thrilling to see that launched. And now we're starting to see, they're adjusting the mirrors, and we're starting to get some images. Another Goddard in-house project is the Solar Dynamics Observatory, which it's eyes on the sun. It's part of the Living with the Star program. The MMS mission studied plasma and particle acceleration in the Van Allen belts, the Earth's Van Allen belts. And of course, the Hubble Space Telescope has been a workhorse for us, for NASA, and particularly for our astrophysicist scientists. And I was involved in all of the refurbishment missions for Hubble, and that was centered at Goddard as well. So as you can see from this very busy chart, Goddard has a diverse mission portfolio. But one thing that all of these missions have in common is that they are in a radiation environment. And so I've worked on most of them over my career. So for the outline, I'm going to roughly follow my career, where I earned my technical stripes as a radiation hardness assurance engineer. Through my concerns about not having adequate environment models to assess the radiation environment, I started working on the Living with the Star program, and I had the opportunity to see the birth of the heliophysics science discipline through working on the science architecture team in that program. And I really focused in on getting new Van Allen radiation belt models for engineering applications. And then, as I said, I was lured into branch management and eventually became the division manager. So first, I want to give an overview of the high energy radiation environment. This is an artist's conception of the sun and its interaction with the Earth's magnetosphere. So we have the solar wind plasma streaming from the sun. It makes a bow shock with the magnetosphere and compresses it in the solar direction, and then stretches it out into a long magnetotail in the anti-solar direction. So I'm going to talk about 4 families of particles that we worry about. So when we have solar storms, coronal mass ejections, and solar flares, protons and heavier ions are energized, and they're accelerated toward the Earth and impinge upon our magnetosphere. And then, of course, we have the ubiquitous galactic cosmic rays, which consist of protons and heavier ions, which are a concern for electronics. The magnetosphere protects us, and the atmosphere protects us from most of these particles. However, satellites that are operating in polar orbits or outside of the magnetosphere are treated to the full extent of the particles. Also, galactic cosmic rays, because they go up to energies of GeV, some of them penetrate the magnetosphere and they hit our atmosphere. And as they hit the atmosphere, they start to decay. And one of the decay products that causes radiation problems are the neutrons, and those neutrons are a concern for high altitude aircraft and also on Earth. And then, of course, we have the very complex particles that are trapped in the Van Allen belts that surround the Earth. And these belts are high energy, and they can be extremely intense and are a problem for spacecraft and instruments that operate there. So this is sort of a summary of the characteristics of the radiation environment. As I mentioned, they're very high energy and they penetrate. The solar variability drives the population levels, solar rotation, the long-term solar cycle, and solar storms and magnetic storms makes it difficult to model these. These are all complex processes. As I mentioned, the magnetosphere deflects the galactic and solar particles. However, polar low Earth orbits are exposed to interplanetary levels during passes over the poles. And we have to constantly remind our Goddard scientists and engineers that just because they're in a low altitude, if they're in a polar orbit, they have a moderate to severe radiation environment to worry about. The trap population, the Van Allen belts have a complex spatial and time distribution, and it makes modeling those a big problem. And the environments are relatively stable. However, the abundances do bounce around because of the solar cycle and these solar storm variations. This is an overview of the effects of space environments. So we have plasma particle radiation, neutral gas particles, ultraviolet X-ray, and then meteoroid, the man-made space environment. So the people who work about radiation effects play in this area. So the low energy plasma causes charging. These are low energy electrons. They cause surface charging, and they can bias instrument readings, pulsing, power drains, and especially for high voltage solar rays, they can actually cause physical damage. For the high energy particle radiation, there are three families that we worry about. We have ionizing and non-ionizing dose, which is a long-term accumulation that causes degradation of the performance of microelectronics and of optical systems and degradation of solar cells. So usually we engineer these so that we can degrade gracefully in emission. However, if there are components that are inadequately shielded, or components that really should not be flown in the radiation environment, they can cause an end to the mission. And then a more recent phenomena that we started worrying about in the 80s and 90s and still work on are single event effects. And you've probably heard of these in terms of bit flips or single event upsets. And they can also be destructive. So there are single event latch ups that can destroy the function of the device and end emission. We sadly had one of those at NASA. But most of the problem is data corruption, noise on images, system shutdowns, unexpected shutdowns, and again, these latch ups or gate ruptures or burnouts on power devices can cause circuit damage. So we see the effects of the environment on our systems. These are Terra star trackers. They were in a 700 kilometer, 98-degree orbit, so they were going over the poles. And I got a call, panicky call from this mission after it launched saying that their star trackers were shutting down constantly. And I said, well, show me the hits that you're getting on the star trackers. Just send me the data. All I need is latitude, longitude, and altitude, and I can tell you whether or not it's radiation. And of course, we clearly see the hits coming over when it's passing over the poles in the north and in the south. And then here is our South Atlantic anomaly that's a bulge in the underside of the radiation belts that go down to very low altitudes. And so I drew this contour, I calculated the contour of the greater than 10 MeV protons, and we very clearly see the outline of of the proton. So we know that it's protons and probably heavy ions in the poles that are causing these problems. Fortunately, they were able to upload new software to inhibit the idling of the trackers until the background threshold was exceeded for an extended period. What was happening is that the detector that they use in the star trackers uses a star map. And when they get these particle hits, they're false stars. And so the tracker loses the star map and really doesn't know where to point anymore. Fortunately, we did not lose. We had several missions with this star tracker problem. So I want to give an overview of, this is kind of a first cut that we take when we get a new mission on understanding their radiation environment levels. So we classify them to low, moderate, and high. The low levels are usually less than 10 K-rads, and that's typical of our low altitude orbits. They have moderate single event effects in environment by some of the stray galactic cosmic rays that penetrate. And also if they have a device that's sensitive to protons, they're going to see hits in the South Atlantic anomaly. And they have a low displacement damage environment. So these are the low altitude, low inclination orbits, as long as they're shorter mission duration. And by that, I mean perhaps 2 to 5 years. A moderate environment, we look at total ionizing dose as 10 to 100 K-rads. It's intense single effects environment, and a moderate displacement damage environment. And these are low inclination or low altitude, high inclination orbits. A lot of NASA's Earth observing orbit satellites are in this orbit. Excuse me. And also at L1, Lagrangian stable point in the solar direction, and L2 in the magnetotail. And we have the geostationary orbits we also consider medium, moderate. Excuse me. And then the most challenging environments, of course, are classified high. They're usually greater than 100 K-rads of dose. They have intense single event and intense displacement damage environments. And these are the missions that go to Jupiter, geometric transfer orbits, missions that fly through the intense part of the radiation belts, the medium Earth orbits in the intense radiation belts, or orbits that go, some of them that go very close to the sun. So as I said, I started my career as a radiation hardness assurance engineer. In the 80s, I worked at Goddard Science Mission Directorate in the Data Archive Center, and there I had the opportunity to support Don Sawyer and Jim Betty, who are known for developing the Van Allen belt models, the famous AE8 and AP8 models. And working with them, I saw how they were put together, worked on some of the data sets, and really started to understand that these models needed to be upgraded. There I worked closely with E.G. Stasinopoulos, or Stas, as the people in the radiation community call him. And he was known for his application-oriented research to understand radiation exposure, its effects, and to do radiation environment modeling. He worked with co-op students and developed some great orbital flux integration codes, did radiation assessment for flight projects, and evaluated impacts on flight missions. And he was the pioneer who led the way to understanding how we could transform knowledge, science knowledge, into helping our flight missions. He did the nuclear explosion decay model, the starfish model. He produced the first model for solar proton events, the SOLPRO model, which was based on one solar cycle. And I think one of the most important things he did was he understood that we needed to test parts. And so he worked on developing radiation test facilities, one at Brookhaven National Lab for single event effects testing. He was a proponent for development of shielding and dose deposition codes. And I think most importantly for my career was he really supported participation in NPSS and its related conferences. and worked hard to get funding for us to attend those conferences, which is usually we can't get those from flight projects. These are some of my accomplishments. I worked on the environment models and I developed assessment tools for defining flight project requirements. I wrote radiation requirements for over 35 flight projects. I got pretty good at doing that. One thing I learned is that none of the projects are the same. They all have different science requirements, observation requirements, and they fly during different parts of the solar cycle. So this was a constant challenge to keep up with all of these flight projects. I was able to work with Steve Seltzer at National Institute Standards on the dose shielding code and dose deposition code, which has really become a workhorse for the radiation effects community to understand how to evaluate levels of total ionizing dose. I developed Goddard's expertise with Monte Carlo particle transport codes. These codes have been around for a while. They were used for very high radiation missions. However, as we started using COTS parts and radiation tolerant parts rather than rad parts, these codes became more important for Goddard's missions. I had the opportunity to lead the analysis on some on-orbit testbed data for SRAM memories and power MOSFETs. The purpose of flying these is not to see how a particular device performs, but how accurate are our estimates of the levels of radiation, particularly for single event effects. So it's really a validation of the models that we use to estimate the levels. I expanded a database for solar proton events, which we used later to prove solar proton models. And then finally, I completed a survey of the capabilities of radiation environment models and presented that as a short course at the 1997 NESPREP conference. So in the early 90s, in response to growing concerns about radiation effects on spacecraft and instruments, especially with the increasing use of COTS components and single emergence of single event effects phenomena, Goddard reorganized its radiation groups. So it established the Radiation Physics Office and the Radiation Effects and Analysis Group in the Engineering Directorate. So it pulled together 3 groups from Engineering, Science Mission Directorate, Safety and Mission Assurance Directorate. They put us all together and said, come up with some hardness assurance methodology. So the group lead for REACT was Ken LaBelle, and he recently retired, and I really have to congratulate Ken and give him a lot of credit for pulling these 3 groups together and growing the capability there, recruiting really outstanding people from around the world, actually. And Ken was a great proponent for partnerships with universities, industry, and the Department of Defense. And so within the US and actually internationally, we were able to influence the growth of radiation hardness assurance engineering. Like Stas, he was a proponent for participation in NPS and related conferences. And later he became the co-manager of the NASA Headquarters Electronics Parts and Packaging Program. And through his role there, he was able to get funding for understanding how particles interact with our electronics and work on developing interaction models. So this turned out to be a critical point in the development of Goddard's radiation hardness assurance capabilities. So our group came up with a hardness assurance methodology for our NASA missions. We worked with Jeff Paulson Lab, JPL, on this. And so the definition are activities undertaken to ensure that the electronic piece parts placed in the spacecraft systems perform to their design specification after exposure to space radiation. Simply put, please keep the birds in orbit. So the goal is a system tolerant to the radiation environment within the level of risk that is acceptable for the mission. And people are attracted to hardness assurance because it's multidisciplinary. It involves particle physics, device physics, materials engineering, parts testing, understanding electrical systems designs, and also reliability and fault tolerance. And this certainly is what attracted me to the discipline. And this methodology evolved at Goddard with the need to qualify COTS components and also radiation tolerant components for flight missions. But we really were looking at a paradigm shift where we went from risk management versus risk avoidance. If we use all rad hard parts, then we're avoiding risk, but this became less and less practical for missions. And the drivers for the methodology, as I mentioned, were the COTS parts to meet demanding mission requirements. And also rad hard devices are older technology, and often they can't meet the mission requirements as designed by the scientists. Also, there's a reliance on radiation tolerant components, and there's a niche market of suppliers for those components. And we work closely with those suppliers to make sure that we have components that we can use in missions. Also, there are long lead times for radiation hardened parts, and they're very expensive. This is an overview of the methodology. In this box, we have to evaluate the level of radiation failure, whether it's dose, non-ionizing dose, or single benefics. And it involves testing the semiconductor at radiation test facility using standard test protocols. If they exist, often we go to a facility and see a new phenomena. And so there really isn't a protocol. We have to kind of fasten our seatbelt and ride it out. And then after we get the test data, we estimate the level of the response for the mission radiation environment using a predictive model for the effects of the interactions of the induced environment with the semiconductor, if there is such a model. Again, it were kind of fly by the seat of our pants, so to speak, in this box. And the other box, another important step, is defining the radiation environment and then defining the environment at the levels within the spacecraft. And we put all that together and we categorize the part as to not acceptable, reject, and go back and look for new parts. If it's hardness critical, then we always recommend doing flight lot acceptance testing, or hardness non-critical, then it can be approved. So the big issue here are the radiation design margins. So these margins can be, if we have good models, ×2, but they can go up to ×10. And so there is a lot of design margin in here and in here. So these are rules of the thumb for radiation hardness methodology. I teach classes. I taught a class, a graduate school class, taught on spacecraft development. The students always like rules of the thumb. So these are some of the rules of the thumb. Radiation hardness assurance is not a component issue. It needs to be accomplished at the systems engineering level. The environment has complex distribution and variability. And so the environment definition for Project A will not work for Project B. We always recommend that we use radiation hardened parts in critical systems, for example, our flight computers. Commercial devices can fail at dose levels below 5K rads, and we saw from our total dose classification that most missions experience more than that. And additional shielding is not a cure-all. These are high energy particles, particularly for the cosmic rays, and so they will penetrate right down to our sensitive circuits. And we always tell programs, they don't always listen to us, to start early to avoid retrofitting, redesign, and panic when their parts don't qualify and they're already in past critical design review. So we were able to grow a NASA team of people who were trained in radiation hardness assurance methodology. And this is a picture at the Nuclear and Space Radiation Effects Conference in 2000 of the team. And on Thursday, NASA used to have Hawaiian Shirt Day so that we stood out. I think the culmination of this was a seminal paper that was published in the TNS, the IEEE TNS, and it brought together all of the ideas of emerging radiation hardness issues and NASA's approach for those flight programs. So of course we had hurdles to success, technical and programmatic, outdated radiation environment models, rapid emerging technologies, insertion of COTS, the emergence of the single event effects phenomena, and small sample sizes for parts testing. And all of that leads to large radiation design margins. As I said, they can be minimum of 2 and go up to a factor of 10. And what we really needed were models and test methods that, rather than using design margins, we can have estimates with confidence levels. And that way we can take the problem to the project manager and the scientists, and they can look at confidence levels and make their decision based on that. Also, programmatic, everyone has the same programmatic issues, project budgets, lack of opportunities for on-orbit validation, shortage of the test facilities, shortage of trained personnel, and excuse me, when you're doing mission support, there's a lack of support from the missions to do research and attend conferences. So I talked about the design margins here involving with testing and estimating the level of response. And there's a tremendous people out in the industry, universities, and government agencies who are working on these, and we were fortunately able to recruit several people to the group who tackled this problem. So the box that I decided to play in was defining the hazard and the definition of the environment within the spacecraft with the goal of reducing design margins. So the first cut we take at doing a total ionizing dose is with the shield dose code. And in this example, this is the glass instrument, and they were concerned about their LiDAR detectors. And in this code, we just use generic geometries. And to get a worst case estimate, we use a solid aluminum sphere with a target in the middle, shift the environment at it, and then estimate. And then they get a dose estimate. This is a top level dose estimate. So we usually use average box thickness of 100 mils of aluminum. And in this case, we got 10 K-rads, which is really pretty low. However, the glass mission had picked some LiDAR detectors that were very sensitive. So we had to improve our dose estimate by using the 3D ray trace. And this is a model. This is a model of the instrument, and there were several detector locations. I think I put maybe 20, 30. And so this represents the spacecraft. At that time, when I was using this, we had to develop these models with blueprints, a ruler, and a drafting table. And so it was very expensive and time consuming to do the spacecraft. But we can do a rough estimate of the shielding provided by the spacecraft by taking a conservative smear in the spacecraft shape. So we take the mass and we do a conservative smear of the mass, and gives us an approximation of the shielding provided by the spacecraft without having to model it. And as you can see here, I think our highest point was about 2 K-rads, and so we were able to qualify these parts. So in '96, Stas and I decided that we needed to lease this 3D Monte Carlo ray trace code. We use EMP's novice code in anticipation for the increased usage of COTS components and missions. Well, as I said, it takes into account the shielding. I first used it for the FAST. It was a small cost SMEX Explorer. And Even though it was low cost, it was in a very intense radiation environment. This puts it through the most intense proton environment. So they were going to have a high total dose. Unfortunately, they started late in the program. I think they were past heading toward critical design review and getting ready to cut flight hardware and already chosen their parts. However, I was able to use Novice so that they could qualify. In this case, there were memories in the flight data recorder. And now it's standard practice at Goddard to use Novice in Phase V of mission development in preparation for preliminary design review. Here's the radiation structural model for the SDO. And you can see it's much prettier than the model that I had to produce with blueprints and rulers, because now that we can ingest into the code the mechanical design for the spacecraft and instruments. So the next part was not so easy. It was tackling the errors in the models. And I just briefly want to mention galactic cosmic ray models. We had pretty good models, thanks to Jim Adams and his group at Naval Research Lab. They had just single event effects had come on the scene, and they worked on this model to address single event effects issue. And this was a baseline model, and we used, as the model progressed, they used different ways to modulate the solar cycle. And finally, there's a fit to some sunspot numbers. So we have pretty good estimates of the galactic cosmic rays throughout the solar cycle. I mentioned that the SolPro model, I was working on a database to expand that model. And I met Mike Zapsos and Ed Burke at a conference, and they had also started working on the models, and they were using maximum entropy principle to fit the event distribution, which is used for earthquake predictions. And they are, it's an important way to get a distribution when you have an incomplete data set. And then they used extreme value theory to estimate the largest events, and they got data for solar cycles 20 through 23. So this psychic, excuse me, the psychic model is a really good model. I need to get some water. Done? Sorry, I'm back. I was barking at my husband. But he was listening to the talk with his headphones on. He couldn't hear me. And this model covers the full energy range of solar protons. And then they did the same thing for heavy ion, solar heavy ions. The real modeling problem, the huge problem, were the trapped radiation belts. This is an artist's conception of the Van Allen belt. Here is the inner zone, which is dominated by high energy protons. And then this massive outer zone, which is, it has lower energy protons, but it's mostly electrons. And so to better understand the distribution, I'm plotting the proton and electron intensities with the AP8 model, the AE8 model. So here's our proton belt, the inner proton belt. So you can see that goes up to 10 to the 6 in the intense regions. So any mission flying through there is going to have a high total dose and high displacement damage problem. And then here is the massive electron outer belt. Well, the inner belt, there are also electrons in inner belt, but the real business is out here in the outer belt. And so if you look at, this is L shell, which is Earth radii, distance in Earth radii along the magnetic equator. And this is geostationary orbits are right in this region. So they get blasted all day, every day with high energy electrons. And then, of course, even more intense are the flights that go through spacecraft that go through the medium Earth region. So those, they look nice and stable, but they're not. Storms affect them. So you notice that there was in the artist conception, there's called the slot region between the inner belt and the outer belt, which the models show is pretty devoid. However, here I'm showing some electron measurements from the SAMPAC satellite. So this is time. Again, this is the distance in Earth radii from the along the magnetic equator. So the models show, and measurements match the models here, but then we get this storm, a solar storm, we get a huge injection of electrons, and it populates this so-called slot region, and then it enhances the levels down in the inner zone. So this is a real problem for modeling. And one of the things in my survey, model survey, was I looked at the AEP and AE models and understood how they were put together and the data sets that went into them, and realized that they were impractical to update. They're data table models. There's no physics in the models. They're based on long-term averages, 4 to 6 years. So they have poor time resolution. There are large uncertainties for some reason in some regions. So the spectra, often the energy spectra were often extrapolated. They didn't exist for some energy ranges. And these energy extrapolations in the low energy regions are a particular problem for materials qualifications. So the models, they were great when they came out, but they lack functionality for contemporary applications. The average and worst case are not sufficient. They have limited application to single event effects problems, and essentially they're useless for charging analysis. So I started talking to everyone who would listen to me, and actually some people who didn't want to listen to me, about the need to get international science, modeling, and engineering communities to work together. So as I said, I performed a survey and presented a short course. I briefed international and national space agencies, the US Department of Defense and Research Council. And I started writing papers and writing presentations to highlight the problems with these models. And also I noted that the space climate models identified in the US Space Architect, it was identified as a gap in the US Space Weather Program. And then I worked on the US Space Technology Alliance working group. And that was the #1 priority out of that working group. And also European Space Agency identified in their roadmaps as a need for new models. So about that time, the Living with the Star program came along, and that was a real turning point, not only in my career, but in our push to work on trapped Van Allen belt models. So I got involved with the Living with the Star program. It emphasizes the science necessary to understand the aspects of the sun and space environment that most directly affect life and society. And I had the opportunity in about 1999 to brief the Sun-Earth Connection program at NASA Goddard, or NASA headquarters. So Dana Brewer was a program executive. She was a huge advocate for space environments and effects research, including flight test beds. And George Withrow, who is the director of Sun-Earth Connection, was also at the briefing. And it was really his brainchild to develop the Living with the Star program, which was science with relevance to society. He is a solar physicist, and he was excited about all of the data that I had showing solar, the variability, that the variability in environments were driven by solar variability. So I was invited to be a member of George's pre-formulation team with Living with the Star, and he asked me to be the liaison between science and engineering communities, which is where I like to live. So that was really great. George kept me plenty busy, that's for sure. I led the practitioner community to define program requirements and foster support for the program. I organized and chaired the user requirements workshop. It was a co-author of the proposal to NASA headquarters that resulted in NASA receiving funding for the program. The White House was briefed, and President Clinton at the time really liked the program and kicked it off to a pretty fast start. I was appointed to the science architecture team, and George told me, you know, it's your job to keep the scientists honest so that we get what we need out of the program. And the result of that, that team's work was a document, a report of the Living with the Star science architecture. As I said, Dana Brewer was interested in test beds. I had had a previous experience working on test beds, so I was appointed as the project manager for the space environment test bed project. So I worked closely with Dana and George to communicate NASA's role to the space environment and effects community, and did papers and presentations with them. And then worked also because of the importance of the geospace part of the mission. And these became the Van Allen probes. I worked closely with that science team to make sure that we got high energy measurements that we needed. Plasma drives the whole dynamics of the system. But I told them that you need to also understand your high energy particles, whether or not you're getting high energy particles. So I made it a science thing rather than an engineering thing. So we ended up with the program of these two missions, IRIS and the Solar B program, became part of Living with a Star. We got the new missions, the SDO, Solar Dynamics Observatory, Van Allen belt probes, a balloon mission to also study the effects in the atmosphere. And then, as I said, we were lucky to get a space and environment test bed out of it. So I decided I had finally gotten a platform to speak from. And so I went to the Living with the Star scientist, Dave Syback, in 2003 and said, you know, we need to have a working group meeting. And this for new standard radiation belt and space plasma models. So he agreed to do that. It was funded by the Living with the Star program. And the funding was important because this was the first time that we got international science modeling and engineering communities together to talk about developing these models. And for the engineering community, I wanted industry there. They usually do not have travel support other than to go out testing. And so we actually paid for their travel and in some cases their time to get them there to really help us hammer out the requirements for the models. So the goal was of the workshop was to report and document progress, get the modelers talking and exciting and talking with the scientists and getting excited about a new modeling program. And so we did. It was 3.5 grueling days, but we did complete the roadmap. And the first part was to establish spacecraft industry requirements. So these are the industries that I was able to get there, and they did a terrific job. So the workshop report was used by agencies to define a program, and Greg Janae, who was just a tremendous leader in understanding radiation belts, he was at Air Force Research Lab developing instruments that were small, that could be put on small spacecraft to do measurements. In fact, those instruments turned out to be an excellent database for that new AP9 and AE9 models. And so in the end, Greg was able to get funding, and the development was led by Aerospace Corporation, and this was an international effort. So this is the top level requirement. I'm going to go through these pretty quickly. Perform mission at any point in the magnetosphere at any time, and it should assess for any orbit, and models needed to be standardized. And so they gave us some great requirements on orbit and time coverage, time scale requirements, which was very important for designing the missions and designing the models. And particle energy range requirements. And we really emphasize this because it's hard to get high energy proton and electron telescopes on missions. So it took from the 70s to 2014. In fact, I think 2 months before I retired in 2014, I was thrilled to get an email that was announcing the release of the new AP9 and 89 models. Paul O'Brien at Aerospace Corporation led that team, and we ended up with Monte Carlo scenarios for flux along arbitrary orbit. So we can ditch our radiation design margins for the environments and give the mission managers confidence levels, and so they can make better decisions with confidence levels. We added, they added 11 additional instruments, and also the models can ingest new data. So we're looking forward to the Van Allen probe data to further update the models. And a lot of these new instruments came from Air Force Research Lab missions. That was so, and then likewise for the protons, we had 8 additional instruments and their confidence levels. So the Van Allen probes launched with the high energy relativistic electron proton telescope. Thrilled to keep that on board. And so this is the one of the Van Allen probes in integration and test. API was a developer of these missions, and they did a fantastic job because they had to fly through the intense parts of the environment. As I said, I'm briefly going to talk about branch management. I became the associate branch head because I wanted representation for the radiation group at the branch level. And there I managed not only the radiation effects group, but also the flight computers group. So that was a huge learning curve. I had to manage development of in-house and out-of-house flight data systems. So we did the Solar Dynamics Observatory, James Webb, ST5, and the Burst Alert Telescope instrument avionics. At the same time, I was project scientist. This was considered a half-time job. I really had 2 full-time jobs. I was a project scientist for the Living with the Stars Space Environment testbed and led the mission confirmation at Goddard's Program Management Council and at headquarters. And it was approved. We selected experiments. And I was also able to negotiate a no-cost spacecraft manifest and launch with the Air Force. Later, a few years later, I became the branch head, more avionics. I think I was there for the full definition of the development of the LRO, command and data handling system. We mentioned these 2 missions, MMS and GPM. And also I had to manage technical oversight for avionics for all the out-of-house programs, the radiation hardness assurance engineering. And also we have to have fun. Engineers have to have fun too. So we developed new technologies, including spacewire. We got spacewire added to our missions and some high-speed computing. So this is a picture of the JWST, Instrument Command and Data Handling. This was a huge project. It was a redundant, so we had 2 boxes developed, plus also we had to do all of the engineering models. And, you know, we end up with this, this nice tidy box, but people forget that also you need racks and racks of ground support equipment that has to be developed. So we have to be able to simulate the spacecraft, simulate the instruments, monitor our box as it's going. So there's a lot of engineering that goes in this as well. So I guess I did well enough doing that to decide to give me the whole electrical engineering division. There I had 9 branches. So in addition to the area where I was comfortable, I had to learn about power systems, instrument electronics, particularly FPGA, using FPGAs for instrument electronics, the electrical systems, and my big learning curve was telecom. I had 2 telecom branches. I used to go out to lunch with them branch managers try to learn something, and I just get it, and then suddenly the tide would just go out. And then we had to put all the bits together in our division. So I also had the flight systems integration and test branch, and we also had an electrical engineering branch at Wallops that supported small missions and the Wallops launches. So it was a big organization. I had 260 civil service employees, big services contract to manage, and about another 300 on-site support contractors. When I took over the division, every single division deliverable was on the project's critical path, which was not a comfortable place to be. And so I was able to build up the management team. I got a couple of extra hires at the management level. And with the 18 months, we were off the critical path for almost every program. These are the launches that came out. These are the projects that came out with the launch dates of the mission of the division. The most challenging project was the MMS mission. So we had the MMS mission were 4 spacecraft. And so we were responsible for the delivery of hundreds of electronic flight units across the division. We were also doing integration and testing for the 4 spacecraft, and that was quite a ballet that was choreographed by Joanne Baker, who's just an incredible integration and test engineer. And I was also, as if I didn't have enough to worry about, I was also appointed as the lead for the engineering directorate support to the project management for all of the flight system development, including the comm systems and the mechanical systems. I was a member of the engineering directorate technical review team for James Webb, so it was really terrific to be able to stay involved with that program. And as I said, engineers have to have fun. We proposed a laser communications relay demonstration in December of 2021, and it got funding through cross-cutting technology program. And this was an engineering division partnership with MIT Lincoln Labs. So here's 3 of my babies. This is the GPM spacecraft as it was finishing integration. As you can see, it's a monster. This was the Lunar Reconnaissance Observatory, which was also an in-house build. And here are our 4 MMS spacecraft, all stacked up, ready to go into the launch shroud. It's like layers of a birthday cake. Getting that thing put together was a tremendous accomplishment. I want to end by talking about diversity. Diversity is deliberate. It doesn't just happen. It has to be a deliberate effort by management. These are the pictures of the current electrical engineering division team in 2022. And as you can see by looking at the pictures, this is not the days of the black skinny ties. My brothers tease me about working in the black skinny tie world. Those days are gone. This, as you can see, this is a diverse team. I've worked with a lot of them in developing their careers, and because of the diversity, it's a strong, robust team. It has really flourished over the past 10 years. So I'll end with acknowledgements. MPSS was a big part of my life. Albie Larson, Hal Fletcher, and thank you, Chinzia. I can't put names for the Radiation Effects Steering Group because there are too many wonderful people there. Also, special thanks to the university with Radiation Effects Graduate Studies. We're able to liaison with them to do some of the research that we need to reduce design margins, and these are some of the universities. There are also international universities who have developed radiation effects programs. Living with the STAR program, Aerospace Corporation and Air Force Research Lab were absolutely instrumental in getting us new Van Allen belt models. I had great mentors, including the well-known Stas. And the electrical engineering division, I built up this support team. I think a lot of you in radiation will recognize Anthony Sanders' name. He is now the division chief there. And we developed a great esprit de corps on that team. It was, we all supported each other. We worked together, we laughed together, we cried together sometimes. And then the radiation effects and analysis group, which is strong and happy. And of course, my amazing husband who put up with all of that through the years. And that is it. So thank you. And I don't know, hopefully we have a little time for questions. I knew I was going to go over. Let me see, I'll stop sharing.
Thank you very much, Janet, for the very, very inspiring talk, as usual. So Bozena can now moderate a couple of questions if we have maybe time for a couple of questions. So from the audience, thank you all.
Thank you so much, Janet, for this inspirational and motivating talk. But also, I couldn't stop thinking about that contribution that you made, that collaboration that you set up, and that international, global, all those show the power, beauty, and excitement of the area that you represent.
Yeah.
And it's just amazing. And I open for questions. I would have many questions, especially in the area of that radiation and area of the risk. And you mentioned before a shortage of test facilities and all kinds of training and all kinds of, as probabilists, I cannot think more about the probability of any kind of nuclear disaster, radiation disaster, and so on. So, but I open to audience. Audience, you have terrific audience. You have outstanding, extraordinary audience. This also shows incredible opportunities, challenges that IEEE offers. So any question from audience? You can unmute yourself and ask question. I don't see any in chat box. But whoever would like to be first with question. And
I can start maybe, Bozena,
sure,
if you don't mind.
Sure,
So,
please.
Janet, as Bozena said, many questions, of course, come into mind, but then I will go with a very generic one. So what is really the next step, in your opinion, in space missions? So do we need really new materials? And of course, I'm projecting that towards what seems really to be the next generation of space missions, humans in space. So do we need new materials? Do you need new designs?
Of course we do. We have, because of the commercial electronics market, the consumer market, we have tremendous capabilities coming out in terms of the capabilities of these electronics. However, they're not for space flight, and so we need to continue to fund qualification programs, programs that do research into the response of these electronics to space radiation. It's the cycle of science, right? That's why I liked working at Goddard, the Science Center, because the scientists ask the big questions, about the universe, about our environment, exploration. And so we work with them, we create missions, capable missions to answer the questions. And then, I love scientists because they come up with more questions. And the more answers they get, the more questions they have. And the questions, the exploration becomes more and more challenging. So we always need new capabilities in materials and components to meet those challenges.
You have nice question in chat box, if you can see, but I can read for you. Do you think it's better for women at NASA in science related to space travel now, as opposed to when you started in 1970s?
Well, yes, the short answer, it is infinitely better, both, for women and for minority groups. In the 70s, it was just assumed. I heard so many times, I was interested in advancement, I was interested in promotions, but what I got was, well, you're here, so stop complaining. You got in the door, so don't complain, be happy with what you have. But of course I was not, and most people are not. Goddard was a comfortable place to work, I think, earlier than in other centers and other industries. And I'd like to say that was because of enlightened Goddard management. However, the African-American engineers and technicians filed a class action suit against Goddard because they weren't getting promotions. And I wish the women would have joined that class action suit, but we were a little afraid to speak up. And so they won the suit, and that brought about big changes. One of the big changes was diversity classes. So we took diversity classes, and they were required for all managers and all influence leaders. And it was eye-opening for a lot of people to understand the historical laws in the U.S. that really hurt advancement of minorities. We also did one for disabled people. They didn't have the guts to do one for women. They were afraid that they would open a Pandora's box. But the women benefited from that class action suit. So everyone was treated more equally.
Now, another question, very nice question, and I would even expand this question. You have such incredible collaboration and the team. So I would be interested, what background those people have, whether I assume interdisciplinary. I assume that you expect certain skills, but here is a question. As a current college student, I am curious about how your education led you to choose the career path of radiation specialist. Very good question.
Yeah, it's a good question. So I was a math
Thank you,
major.
Zach, for the question.
I was a mathematics degree, and I also had a lot of physics and computer science background. And when I was ready to start professional work, my husband and I had moved to the Washington, D.C. area. And I was open to almost anything. One thing I knew that I didn't want to do was to work on, like a computer program to program a better way to get money, out of the ATM machine. I was interested in science applications, and Goddard was here. And I saw an opening. Actually, I was a contractor at that time and applied for it. I interviewed with Stas, E.G. Stasinopoulos, and some of the people there, and it just really clicked just at the interview. I knew that's what I wanted to do. So it says that it takes 10 years to develop a radiation hardness assurance engineer, because most universities don't have degrees in that. However, thanks to some of the developments at universities in the US and actually across the world, I'm thinking of, for example, of Vanderbilt, some of the universities I mentioned in my acknowledgements, Vanderbilt, Arizona State, University of Tennessee at Chattanooga, and I know I'm forgetting some, but we're able to kickstart that because they are in their master's and PhD programs in electrical engineering. They are starting to have focus courses on radiation effects. And so those students are grabbed up as soon as they graduate by industry and agencies. And it's also true in Europe. I was able to do a lecture at the graduate school there at Sparrow in Toulouse. And they have a very large, enthusiastic group of students working in radiation effects. So that's great to see. Good question. Thank you.
Excellent question. Thank you. And any other questions? I know that time is over, but it's fascinating. And, in that research, a lot of questions, but we will probably, Cynthia, probably you will close because we are close to the end. And once again, thank you so much. And in those universities have those environmental studies programs, and it's very popular. It's very popular among women. So maybe in that area, environmental is not under engineering, but environmental studies could be somehow maybe connection, correlation, or maybe somehow to reach out to those. Just only
Yes,
just.
I could see those departments doing classes in the basic radiation environment for the students who are also working in electrical engineering and device physics, and who are understanding all those complex processes and how to understand how to come up with great estimates. And the partnership, I can't overemphasize the partnership with universities and understanding how we can get those design margins down.
You demonstrated this, what we always shoot for, partnership among academia, industry, government. Those are absolutely terrific models that you were engaged and developed. Thank you. Cynthia, you can close.
So thank you. I think I could really stay here forever, because there are so many thoughts coming to mind, and how really all those disciplines are crossing together, and how we could really start discussing about cross-fertilization among different fields. And as a matter of fact, different societies, since we're really trying through these events to have all the representation of society and maybe start discussing. This would be really an enormous goal. So Janet, thank you very much. Thank you for all your inspiring career, and students and young people are definitely responding to that, being inspired, and not necessarily only young people, but us too. And I would like to close this.
So could I say I saw that we have some students on. So for students, there are no limits. You know, I went to a little one-room schoolhouse in the rural area of Michigan, and I never dreamed I would be a division chief. But so there are no limits. It just takes tenacity and willingness to learn new things.
There is nice comment from Michael Alice. There is a multi-university workforce development effort now for undergraduates in rad effects. So thank you for this comment, and thank you for all those efforts of just like that collaboration, that multi-university, those multi-centers. Excellent. Thank you.
I'm
Cynthia,
sorry. Yeah, I got you off track. Congratulations on a wonderful program that you've developed for the 25th anniversary.
Thank you, Janet. And thank you all for attending. And before closing, I would like just to say that the next talk is the 11th of March, and we will have a representation from the Aerospace and Electronic Systems Society. And so more on interesting subjects. The title is Cognitive Radars, the Present and the Challenges for the Future, from Maria Sabrina Greco. So please join us to continue these conversations. And thank you very much again to all. Thank you, Bozena. Thank you, the team at WIE, the staff, who is really fantastic in helping through, and for the 25th anniversary subcommittee team. So I think I did.
And thank you to Joredna. Thank you to Joredna for coordinating.
Of course, and for all this incredible work that she's doing. So thank you again, Janet, and see you and talk to you soon.
Yes, I hope so. Stay warm in New York.
Thank you.
And everyone, stay safe.
Thank you very much. Thank you, Cynthia and Janet and Joredna. Thank you.